Okay, so welcome back, everyone. So today is the second lecture by Antonio Longa. It will be about geometric learning, and then I forgot the second part. I don't see your slides. So what's the title of the second part?
Sorry.
Yeah. So So today's will be examples in PyTorch geometric. Thank you. And then, but you have second part, right? You have the title.
Yes.
I forgot the name of the lecture.
Okay. It's hands-on to geometry. So thank you for the invitation. Thank you a lot. It's a pleasure to be here. As you was introduced, this is the second lecture for geometric deep learning, and today we are gonna talk about how to implement simple models on PyTorch geometrics. So this is the same slide of last week, in which the first speaker was Gabriele Santin. Today it's me. Next week is going to be Steve. And finally, Francesco. Okay, here's the pipeline. What we are going to see today. So first of all, we are going to introduce a simple node classification task. And we are going to introduce two models to try to predict in this node classification task. Then we are going to move to graph classification. And in this section, I'm going to go through the data loader object, and we are going to see which are the functions and so on and so forth. And finally, we are going to move to a real-world example using several models. So I'm going to say only 2 words about this real world right now, and then when we will be back, I'm going to go in much more details. So last time, Gabriele introduced you of this problem, and I would like to say that I'm not a mathematician, and I don't want to say something too wrong. So the idea here is that suppose you have a piece of metal or some kind of material, and on this metal or in this material you heated it, and you see how it's propagated, how the heat propagates in this material. And so you can see here in this axis that as soon as, changing the starting point and the material, you have a different spreading. While on this axis, you can see that the model, the mesh used to model this problem is has a much more higher resolution, because the problem is continuous. So we discretize this and we have a much more fine zoom in some sense. We are going to focus only on one parameter, and we are going to see in a simple 2 words, use some of them for train, and we are going to predict on the last one. But don't worry, I will come later giving much more details. The last stuff I would like to say is that for those that are closer to the north of Italy, from the 27th to the 3rd of November, there is going to be the Log Italian meetup. Log is a conference, and it's a free event with keynote speakers, and it's free to attend. If you are closer to Trento and you want some information, there is the link, and the slide will be published. Okay, I think we can start. So first of all, I would like to say that in the Git repository, you can find a folder with part 2, in which you have the data set for the, let's say, real world example. And then you have the Jupyter notebook we are going to use. I'm not going to spend too much. I'm not going to say nothing about the installation, because it might be dependent on your system, on your, or in your operating system, and so on and so forth. But there are plenty of tutorials, and even from the official library, in which tells you how to install the PyTorch Geometric on your machine. Okay, so this one is the notebook you can find online. And let's start with the node classification task. Here, the aim is that we have a huge graph with some feature on nodes and some labels. And what we want to do is predict, learn on some labels and predict on, learn in some nodes and predict on other nodes. First of all, what we have to do is to import Torch and the functional as f from Torch. And then from Torch Geometric, I'm importing this package for transformation, and then this for the data set. In particular, in the first experiment, we're gonna use this collection of data set. And finally, I'm importing two simples model. Then it depends on your machine. If your machine has a GPU or not, you can specify with command that if the CUDA is available on your machine, then you can specify a device to be CUDA, otherwise the GPU. And once you have done this, go back to the dataset. The dataset has been taken from the official repository. In particular, this collection of datasets contains a lot of dataset, and for each of them, you can find more information. For instance, we are going to use this one that is a collection of citation networks, and you can see that there is the specification how to instantiate the class, and then some parameter to specify. Today, since it's the smallest and I'm running on my laptop, we are going to use Cora. So in practice, once we have imported with this from Torch Geometric.dataset import planetoid, we have simple to call the class, specifying the folder in which I would like to download the file and the name of the file I would like to download. If I execute this, what happened is that, okay, I'm here, is that the framework automatically download all the files and store all the files in this folder. If we go back in this folder, you can see that the Cora folder has been created, and you have the processed graph and even the raw graph. All the information are stored. In fact, if you execute again the same command, the framework, the library, understand that you already have the graph, and so it doesn't download it again. Let's inspect this data set. So if we print this data set, you can see that there is only the name of the file, and then we can move the device, the data set, in position 0 in this case, because it's one unique graph to our device, that in my case, it should be CUDA. Now, the dataset object has, let's start from the data, I think. If you look at the data object, you can see that there is the X feature in which you have all the information about the graph. First of all, I think it's quite complex to inspect those matrices like this, so I prepared this small picture in which, okay, this graph is quite huge, but let's start with this simple example. We have our input graph. For each graph, we have node features. So for instance, this node I called 0 has its own features, and we have direction on this graph, and so on and so forth. Then we have labels. So each node has a label, okay, that in this simple case could be blue or red. And finally, we have our train mask and our test mask. I'm not using the validation mask for simplicity right now. Okay, but which is the relation between this object here and this idea of graph we have? Well, let's start from the X. The X is simply a tensor that contains the number of nodes times number of feature. What does it mean? It means that each line represents the feature of the node of a node. And indeed, if we try to print data.x, we have this tensor that in our case, so in the core example, is 278 nodes times 1,433 feature per node. Okay. Then what we have the edge index. The edge index is simply a list of lists that tells you the edges. For instance, in our case, we have an edge that goes from 0 to 2 and to 1, sorry. And we have...
I have a question.
Sure. Yeah.
Yeah. So what do you mean by feature? Because you say the other one is the nodes. So we know like we have node and edges. So the feature is the edges or what?
Okay, thank you for the question. Well, the feature here can be any kind of information about the node. So in the case of Cora, features represent a bag of words of the article. So associated to each node, you have a bunch of informations that relate to that specific node. As I told you, suppose that this network is a social network and nodes are individuals, then you may have as a feature the gender, the age, I don't know, the institution, whatever you want.
Thanks, it's so clear now. Thanks.
Okay, cool. So back where we have, X contains the node features, edge index contains the edges, and Y contains the labels. So in this toy example, labels were blue and red, and simply the tensor is just, instead of having blue, red, and so on and so forth, it has a number corresponding to it. So for instance, in this case, the label of node 0, it's 0. That means blue in our case. And finally, we have this train mask and the task mask. Why? Because we would like to use some node to learn our graph neural networks and other nodes to test if what we learn is correct. So how those masks are done? Well, they suppose again that in our toy example, we have 0, 1, 4, and 5 in the train set. Then our train mask will be true, true, false, false, true, true. Basically, we are telling that it is a simple Boolean mask that tells you which node belongs to the training mask and which one belongs to the test set. And okay, I hope this little example is clear. So
sorry, I have a question.
Sure.
So when you say train mask, does it mean like when you're training, you only take information from those nodes and not the others?
Exactly. In particular, when you are computing the loss, you are propagating the formation even through test nodes, but the loss is computed only on training nodes.
So it's like it's an independent function of the test node.
Exactly. Yeah.
Right, okay. Yeah. Thank you.
Thank you. So back on our object, we have our data. We already saw that the X contain these features. So the tensor is quite huge. So you can see only zeros, but I mean, there are numbers inside. And then we have our edge index. So simply edge index. And here you can see that, for instance, there is an edge going from node 0 to node 633, from node 0 to this node here, and so on and so forth. Then we have our labels that in this case, for Cora, I didn't tell you, but it's, if I remember correct, it's 7 classes. So it means that we are not in a binary classification, but we have 7 classes. So each node belongs to one of those 7 classes. And then we have our masks. Let's take, for example, the validation mask is simply a list, a tensor of false or true, depending on the node goes in that direction. Okay, I hope this concept of the dataset is correct. We have loaded it. So far, we have our data object, and it's time to move to the model. The model is going to be...
Sorry, I have a question.
Sure.
Is this the only way to represent graphs? Like, is this a standard way to represent graph data?
Well, in PyTorch Geometric, yes, because when you have a graph, you can store it as a diasynthesis matrix or as an edge list. But in PyTorch Geometric, when they developed it, they decided to implement this. But you have functions that allows you to convert graphs, I don't know, from network X to PyTorch Geometric, from PyTorch Geometric to network X. So there are different ways to achieve this graph.
Yeah, thank you.
Thank you.
So the same representations applies also for knowledge graph. I don't know if you have.
So we're going to have a specific session on knowledge graph, but the idea is similar, with the difference that you have also to store node types, if you have it, edge types in a meaning, in the sense of relations, because you may have relations to specify in a knowledge graph. And so you have multiple of those objects that has different informations. Later in this tutorial, I'm going to show you mutagenicity. That is another dataset for molecular properties. Doesn't care right now, but those dataset has also edge features. So you have information on the edge that in that case tells you the bound between two atoms. But what I would like to say is that you can represent multiple information, but the idea of the object is the same. I hope it's clear.
Yeah, thanks. It's clear. Yeah.
Thank you. So it's time to move to the model. Back again to this simple graph toy sample. How is going to work? Well, we have our graph. We have a first convolution and a second convolution and the prediction. It's quite simple, straightforward. Let's zoom in a little bit in the first convolution. Well, suppose that we would like to learn a representation for node 0, and we call this representation x prime of 0, okay? How it works? It collects, x0 collects information from x1, x2, and x0, because many models, not all of them, but many models add a self loop on each node, so that when you are propagating information through the network, you also propagate your own message, okay, to achieve this, to build the new representation of the node. So I don't know if you can see or it's too small, maybe, okay. Okay, so here the idea is that we have our input, the node feature of node 0 that is 1433 times 1, so the entire vector. We have a similar vector of the same size for node 1 and for node 2. Those are multiplied by a weight matrices, okay? And then, this matrix is shared among all the nodes in this convolution. And what happened after this operation, we have an ordering invariant aggregation. What does it mean? It means that, for instance, the sum is ordering invariant, because we will like that the ordering of 0, 1, 2 or 2, 1, 0, the result will be the same. And this is why we need these graph neural networks. So here can be a sum, can be an average, can be a maximum, this kind of operation. And then we have a nonlinearity. At the end, what we will have is a representation after one convolution of node 0. And I call it x prime 0. In particular, in this toy example, I'm starting with this feature that is 1433, and I'm compriming it up to 20 times 1. Okay. Then what happened? We have the second convolution. If we have a look at the second convolution, now we have that we would like to compute x second of 0. So the representation of node 0 collecting information from two neighbors, I mean, two hope distance neighbors. And what we do, we repeat what we did so far, but instead of using the input features, we are going to use the learned features so far. So we will have, instead of x1, we will have x prime 1, x prime second, x prime 0. And once again, we multiplied for a matrix that is shared among all the nodes. And then, once again, we will have this ordering bar aggregation, a non-linearity. And if this matrix, W2, moves your embedding from 20 up to 2, at the end, in your last representation of the node in your output layer, you will have a tensor with two elements, in which in the first elements you will have the probability, but then we are going to see why I'm saying probability, to be a blue node or to be a red node. And this is the general idea of the model we are going to implement. Is it clear so far? Do you have doubts? By the way, if you have...
Yeah, it's clear, but I wanted to ask about x prime nodes. So how you get 20 and 1 is...
So, yeah, sorry, you're right. Thank you for the question. The idea is that here in the first section of the image, I showed you how to compute x prime of 0, but you have to compute this x prime for all the nodes. So you will have x prime 0, x prime 1, x prime 2. In the case of x prime 1, you will see that its own computational graph, because this structure is called computational graph, as contains, it will be, I mean, collects information from x5 and x1. And so once you build this node hidden representation of the node 1, 2, 3, 4, all the nodes, then you can move forward in the next convolution and compute x second 0, x second 1, and so on and so forth. Does it make sense?
Yeah, but my question is about the 21 up to x prime 0 is the same with x prime 1, x prime 2. You have 21.
Okay, sorry. The idea is that this matrix here, when you multiply the node vector times W, the shape of W is gonna produce a vector that has different size. So if W is 1, 4, 3, 3 times 20, once you do this product, the output is a vector of 20. And this is an hyperparameter that you can choose. And it's often called the hidden channel dimension. So it's something that you are going to test. And the idea is that you start from a really huge node features and slowly you compress it up to achieving the number of class you would like to have. And so to answer to your question, this W allows you to compress information and of the node representation to learn a new representation of the node. Is it clear now?
Yeah, it's clear. So I see it's related to the convolution or to the filter you're applying.
Exactly.
Okay, yeah, thanks.
Thank you.
So I have one question.
Sure.
So why are we like multiplying each of this node with W1? The x0, x1, and x2, each case we are multiplying with W1. But in a feed-forward neural network, we can see that we apply different weights to the different nodes. Can you really explain? Sorry if the question is naive.
No, not at all. Well, the standard feed-forward message passing uses the same weight matrices for all the nodes in the first convolution. I don't know if you can see it, it's quite small, sorry for it, but in the second layer, we will have another weight matrices. So another bunch of parameters we are going to learn to use. What one can do, and it's often used in, as far as I remember, in heterogeneous graphs, in which you can choose that for different node types, you could use different weight matrices. So in such a case, it can be seen as having multiple of those Ws. Another example could be, suppose that some nodes has features as I don't know, 20 features, while other nodes have 100 features. So either you do a padding to have the same dimension of feature, or you can use, as you suggested, different Ws.
That explains it. Thanks.
Thank you. So let's move to the code. The code is quite simple. So we are gonna see this variable later, but don't worry. First of all, we have to define the class. Defining the class is simply class, the name of the class we would like to give, for instance, GCN. The class inherits from torch.nn.module, and there is this, the init of the function has to take the self, so itself, the in channel, the hidden channel, and the out channels. Of course, here you can add other parameters. Then what we have to do, we have to call the superclass, the one in which we were inheriting, and then call the init function. Then what we have to do, we are defining two convolutions that are simply just calling the GCN conv layer already implemented in PyTorch Geometric. I maybe did it too fast here, but in order to import it, it's on the library, and there are several parameters you can exploit. For instance, let me open just a second. We are using GCN conv, and here is a small explanation, and then you have all the parameters you can set. I'm gonna try to be as simple as possible, not to lose, too much time on these details. So I'm specifying the in channel, the hidden channel. The hidden channel is the size that we are choosing, the 20 I fixed above. And then what we have, the second, that is identical, with the difference that the input right now, it's the hidden channel, so our 20, and the output channel is what we are passing. In the forward, what we have, X, that are our node features. We have our edge index and an edge weight if we have it. In our case, we are not going to have it, but doesn't matter. The idea is what we do. Simply, we call our convolution, the one we defined above, with X, the edge index, eventually edge weight, and then we apply a ReLU, in this case, a nonlinearity, obtaining an X, and this X is fed again into the second convolution, and we return the X. The model is quite simple. I mean, most of the code has been done within the GCN conv layer that has been already provided by PyTorch Geometric. Okay, now we have to instantiate the model. We just need to call GCN, specify the in channels. Now, the in channels are exactly the number of node features, and we can access them by simply saying num of features. And indeed, we have 1,433 features. So our first input channel is going to be that dimension. Then we have our hidden channels that we choose to be 20. And finally, we have our output channel, in which it's the number of classes we have. In particular, if I remember, it's 7, okay? Once we have do this, so just basically call this function here and passing these 3 parameters, we move our model to our device in order to execute the GNN on our CPU or on a GPU. Then we have to instantiate the optimizer. We are going to use the Adam optimizer. You have to specify the parameters, and in this case, we are just simply to access the model.parameters. And finally, I've specified this learning rate. You can specify away decay. You can specify a lot of stuff here. But it's just like, I mean, if you see, this one is not anymore a PyTorch geometric object, but is a PyTorch object. So here you can do what you can do in PyTorch. Okay, I'm printing the model. You can see that the model is a GCN with 2 convolution. The first convolution is a GCN convolution with these parameters. And then we can access this information, for instance, model.con1, and we see that this one is our convolution, and we can access weight, we can just a lot of information from here. Okay, the definition of the model, is it clear? Can I move forward?
I have a question up there about the output. You say the output is equal to dataset dot number of classes. So the number of classes is already known, or
yes,
or you have to precise it?
No. Well, when you build the data set, you will, sorry. The task here is to predict a specific property of the node. And when you build the data set, you already know that there are 7 features to predict. Sorry, 7 different categories, 7 different labels. And when you load the data set, this number is already specified. Or if you are building your own data set, you can specify it when you build it.
Okay, thanks.
Okay. Here I'm defining 2 simple functions for training and for testing our graph neural networks. So how it works? Let's start with the training. First of all, we have to move our model in training mode. And this is done by simply doing model.train. Done. Then we have to apply the 0 grad to our optimizer, as we do in PyTorch. And then what we do? We compute the prediction of the model. And look here, we are specifying an X, an edge index, and edge attributes that is going to be none, but doesn't care. And here we have a prediction of our model. And then what we do, we use a cross entropy to compute the loss between our output and our data.epsilon. So we are training our model. In fact, if you have a look here, we are filtering the computation of the loss only on those elements belonging to our training mask. And then we apply the loss backward and the optimizer step. And we return the loss. In terms of testing, what we do, it's quite similar. The difference is that the model is not in training mode, but it's in evaluation mode. So we compute the prediction, okay? And then in this case, okay, I'm computing for both the test mask and the train mask, and I'm computing the accuracy simply using, calculating the accuracy. Note that different from previously, here I'm applying the argmax. What does it mean? Let me show you this with an example. So suppose that here I'm computing my output, okay? Now, if you have a look at the output in position, for instance, 0, we can see that those are the representation, the last representation of our model. It's not trained so far. So what we are doing, we are applying argmax so that instead of having this entire vector here, what we do, it returns only the value that is maximum. So this one, the position in the one in position number 2. And this is needed for us because when we compute the accuracy, okay, on the test set, we are filtering, when we are computing the accuracy, we are using data.y that contains the single label for each node. And the only difference between test and train is simply this one. So here in the training, of course, you have the optimizer step, the loss backward, the optimizer step, zero gradient, and so on and so forth. While in the evaluation, you just compute the prediction, you take the maximum, and you compute the accuracy. Once you have done here, once you have done this, okay, what you can do is simply iterate for a specific number of epochs. I'm gonna do 50 epochs, just for example, and we don't need any more, anyhow. Computing the train of our model, train our model and computing the accuracy. And every 10 epochs, I'm gonna print the number of epoch, the train accuracy, and the test accuracy. If we run it, you can see that before the training, so at the epoch 0, we have 0.15% of accuracy in train, and 0.16 in test accuracy. With some time, after 15 epochs, we have that our training accuracy is quite high, and the test accuracy is not so high, but it's definitely much more higher than 0.16. So far, so good. Do you have any questions? Eventually, just interrupt me if you have one. Okay, let's change a bit our model, okay? So far, we have that we were going from 1,433 features up to 20, and then from 20 up to 7. Now we are going to do something different. We are going to go from 1,443 up to 300, and then up to 50. And then we are going to use a linear layer to go from 50 to the number of classes. What's happened here? Here it's here it's different from having 3 convolutions, because here we are, for each node, we are collecting information from 2 hop distance. And then once we have this, we are gonna linear layer to compress this information. So it's quite different what's going on. And okay, we can implement it. It's as before. We have instantiate this class. Sorry, we have instantiated our GCN, with the only difference that now we are specifying even the hidden channel number 2. Indeed, what we have our convolution that goes from our in channel to the hidden channel, then from the hidden channel to the hidden channel 2, and finally from the hidden channel 2 to our out channel. So let's have a look here in the forward. Moreover, we are adding a dropout. What does it mean? It means that during the training, we are removing the 50% of nodes to try to reduce the overfitting. The overfitting is the problem in which your machine learning models is not generalizing, but it's it's not generalizing. And so with this dropout, we would like to increase the generalization of our model. But except for this, we have, as previous, our convolution number 1, convolution number 2, and finally the linear layer. When we call it, nothing different. The in channels is the number of features. The hidden channel is set to be 300. The hidden channel number 2 is set to be 50. And finally, the number of class. If we run it, once again, the optimizer with the model's parameters and the learning rate, what we have here our 2 convolutions and our linear layer. If you see, with respect to the previous model, here we also have this linear layer here. Okay, so far so good. We can execute once again our model. Okay, we have slightly changed our model, and again, in 15 epochs, they are really few epochs, we achieved 0.80 of accuracy, while previous were 0.66. And okay, this part of node classification, it's closed. Do you have any question about this?
So you don't need in your model like the pooling layers.
Okay, we are going to use the pooling layer when we are going to handle with the graph classification task. Thank you for the question. Indeed, the next example is going to be through the use of pooling. So let's move. First of all, we are going to use the 2 dataset. That is a collection of really a lot of dataset. Once again, if you need more information, you have to go to the library, and there is a long list of dataset. I think it was here. And you can download all of those dataset for different topics, different information, and so on and so forth, different sizes.
Actually, I had one question that was, can we use this node classification for binary classification problems, like to predict any particular outcome or disease, like we do in normal machine learning or deep learning?
Yes, if you have a model structure, I mean a graph structure underlined, then you can use a graph neural network to predict a binary classification task. But you need to have the topological structure that connect individuals, in your case, I suppose. Okay, back on graph classification, we are going to import these 2 datasets. Once again, we are setting our device to be equal CUDA or CPU. And then we download the dataset. As done before, if you have never downloaded it automatically download your dataset in this data test folder. And if you execute again, it's not gonna execute again, re-download it. So if you remember, when we downloaded Cora, you can see that was the name of the file and no number inside here. So let me show you really quickly. It was Cora, like this. It means that Cora was a unique huge graph, while here in mutagenicity, MUTAG, sorry, we have 188 graphs. And once again, we can access and see the information. So if we have a look, the totality of the data set has 3,371 nodes, while it has only 188 labels. Why? Because here our task is to predict a property of the entire graph. In particular, this mutag contains moleculars, and the moleculars can be mutagenicity or not mutagenicity. I have no idea what does they mean. I'm not a biology. I'm not in that field. So I know that it's a binary classification problem. I know that each node has 7 features, and that's all. Once again, we have our information, so our features, and that's all. We can even, if you have a look here, we are looking to the entire data set. What we can do, we can simply write, well, data set in position 0. And it tells you that the first graph has 23 edges. It has 23 nodes and 54 edges. And of course, it has only one label. If we would like to visualize those graphs, it's quite easy. PyTorch Geometric has these utils that contains 2 network X. So what you have to do, just to call these 2 network X of the specified graph, and call the function network X.draw. Import network X. Sorry. Okay. It's not super good, but you can see that seems to be a molecular stuff. We have these pentagons connected, hexagon connected, and so on and so forth. Okay, so far so good. So we have these.
Please, on the number of edge you say is 23, but what is the 7?
No, sorry, it was my error. There are in the first molecular, there are 23 nodes, and there are 7 features for each node. So if I access to the dataset in position 0, and I have a look on the feature, sorry, in position 0, here you have that those are the features of the nodes in the first graph.
Okay, thanks.
Okay, cool. Okay. Okay. Now, since we are working with graphs and these moleculars are quite small, we can train in batch. So instead of updating the gradients at each time for each graph, we can collect a series of graphs together, go through the network, make the prediction, compute the loss, and compute.
Can I ask that why the batch size here is 3? Because in the normal machine or deep learning models that we use, the batch size is generally ranges from 32 or 64 like that. So
Yes,
is it
yes,
because the data set is small?
yes. The dataset is quite small, and I would like because I would like to visualize this in a few seconds. So I put 3 only because it's easy to see visually, and moreover, the dataset has only 188 graphs. So, but you are right. Usually, the batch size is much more bigger. So.
Please, can I ask a question? Because I usually don't understand the batch size, what it means. I don't know if you can say something faster before.
Yeah, sure. So the idea is that instead of having a graph, okay, go put the graph through the network to the GNN, make a prediction, take the prediction, compute the loss, compute the back propagation, and so on and so forth, that it's quite expensive. And you can imagine in your surface, in your really complicated surface of the function you are optimizing, you are moving, looking only one graph, okay? So the idea is that what if instead of computed the gradients and the back propagation for each graph, we do it for a bunch of graphs. So the idea is that suppose we set the batch size of 3. What we can do, we send it to the network, instead of one graph, 3 graphs. The networks, the graph neural networks, take in input those 3 graphs, compute the prediction of those 3 graph, okay? And then when you are computing the back propagation using the loss, you have computed the loss using these 3 graphs, not only one. So the idea of using the batch is to, first of all, avoiding the problem to fall down in a local minima in some sense, so that you are not moving in your space for each graph. And another reason is the time required, because in this, suppose that you set the batch size equal to 42, then the number of back propagation you're going to do is much more less with respect to not using a batch size. Does it make sense?
Yeah, thanks a lot. Yeah.
Okay.
Really, I had another question, that is, can you tell a basic difference between the previous node classification and this graph classification? And it will be a bit helpful if you could tell some examples which would fit each use case, means when we will be using the node and the graph classification.
Okay. Well, when you have, it really depends on the on the real world problem you have underlying. Suppose that you would like to classify proteins, okay? You have proteins, okay? You have multiple proteins that do something, and then you have multiple graphs. So what you would like to do is to predict a property for each graph. And so you need to use a strategy for graph classification. While on the other hand, if you have an entire network, let's say Facebook, then the network is a huge network, and what you would like to predict is the property of the node. And then this distinguish between node classification and graph classification tasks. While in terms of data loader, you can apply the data loader on both cases. You can apply the data loader and update the nodes, the gradients when computing on the nodes for every node, or you can do it for a batch of nodes. Is it clear for you a little bit the difference between graph classification tasks and node classification tasks?
Yeah, it makes sense. Yeah, thank you very much.
Yeah, cool. Okay, I instantiate this object that is a data loader. It came from, again, PyTorch Geometric. Here I'm specifying, just for this example, that the 90% of the graphs we are going to use for training and the rest for test, with a batch size quite small, but we are going to change it. So, okay, cool, but how can I represent it? So imagine now to represent those graphs through the use of an adiacenthesis matrix, okay? If you build these super adiacenthesis matrices in which you have the adiacenthesis of the first graph here, and then attach the second adiacenthesis, and so on and so forth, for each of your batches, and in all other points you will have zeros, if you have this big matrix that contains multiple graphs, it's important to notice that there are no edges between one component and the other. There is no an edge that goes from the adiasynthesis 1, so the graph 1, and the adiasynthesis 2 to the graph 2. And so we can represent in this way a much more, an entire object that is a huge adiasynthesis matrices, full field of zeros, and those adiasynthesis on the diagonal. And just to show you what I did here, I put a batch size equal to 3, and then I'm taking one of them, so I'm iterating over our train loader, and I break after the first iteration just to show you. Okay, and then I converted the graph in network X as I did before. I used network X to get the adiasynthesis matrices that is a sparse matrix. I'm using .A to achieve a dense matrix. And then I'm using math-show to show the graph, this super adiasynthesis. So here it's not super easy to see, but you can easily see that this one is the first graph. This one is the second graph, and this one is the third graph. And you don't have any interaction among different components. You can imagine this as having a network with disconnected components. And this is how, and this is how our PyTorch geometrics represent those structures. In fact, if I'm trying to plot this graph, you can see that they are 3 different connected components. Does it make sense?
Yeah, sure.
Fantastic. So let's put here back sides a little bit bigger. I'm not gonna plot it because it's complex to see and so on and so forth. Okay. Now, if the dataset is clear, let's move to the model. So far, what we did, we have a unique graph, we have a model, in our case, these 2 GCN. At the end of those graph convolutional networks, we have a node representation in our hidden space, in our embedding, in our hidden, in our hidden space, okay? And then we apply a linear layer, or directly we apply the prediction to achieve our prediction. So now what happened? We have multiple graphs, but it's not complex, because what happened, we take one graph at a time. We start, for instance, with the first graph, we compute a node representation, and then we have a pooling operator. This pooling operator, what does it do? So first of all, is an ordering invariant function, for instance, again, the sum or the average. And what does it do? Basically, it compresses all of those node representation into a unique graph representation. And then you can apply your prediction. So which are the difference between those 2 models? Well, simply that the second models, once you have computed the node representation, you're applying a pooling layer to compress it in a graph representation. And then you repeat it for multiple graphs. Does it make sense, the model?
Does multiple graphs have something to do with a more complex data set? When the data set will be a bit huge?
Yeah, not only huge, but it may also be another problem. Let me think. Another problem of graph classification different from bioinformatics. Okay, you can have, suppose that you have meshes of animals, okay? So each mesh represent the shape of an animal, okay? So you will have graphs that each graph is a mesh that represent an animal, and you will like to predict which animal is. So in this case, you need the pooling because you need to go from a graph representation, from a node representation to a graph representation. So it's really related to the task you are trying to solve.
I think the example you said just now has something to do with a number of classes when they increase. I mean, which we are trying to, I say, classification for like task for the number of classes, which say it becomes huge. As you said that there were a number of animals, so we can think of them as the number of classes that we are trying to classify,
Yeah,
that which belong to each year.
yes. In this example of animals, you may have different, even more classes instead of only two. But this is just something happening in the prediction layer. So in the last layer in which we are computing the probability of that graph belonging to a specific class. But yeah, you're right.
Sorry, the number of elements in the graph representation is equal to the number of input graphs in the batch.
Sorry, say again?
Is the number of elements in the graph representation, I think it's a list or something like that. Is it the same as the number of input graphs?
No. No, in a sense that the node representation, you have a representation depending on your hidden layer. So the dimension of your hidden layer, and you can specify, for instance, here in the previous example, we fix the number of the hidden channel number 2 equal to 50. So it means that if it will be the case, the node 0 has been projected in some sense in a space with 50 dimensions. And then with this pooling operation, you compress all the node representation into a unique point in the space. Of course, in this case, in the same space.
Yeah, thank you.
Okay, cool. In terms of code, which are the difference? Basically nothing. Okay, first we have to import a global pooling operation. In this case, I'm using global add pooling. I'm using the same network that goes from the input space to 300 to 50, and then the linear layer. So in terms of initialization of the models, we have our convolution, the second convolution, and the linear layer. In terms of feed forward,
Can I ask, means how did you choose the number of hidden channels 1 and the hidden channels 2? I mean, is there a specific rule or do you just choose it randomly?
So this is a quite complex question. So in a sense that usually even the number of convolution you're going to use is an hyperparameter you have to optimize. So when you tune your parameters, you also consider more layer and less layer. Knowing that, it's worth to mention that increasing too much the number of layer, it means that you are collecting too much information from too much distance node. Suppose that
I think, is it something related to overfitting and underfitting, as we have heard in machine learning?
Exactly. I was going on that direction. Is really related to overfitting, and to be fair, there is this problem of over squashing in a GNN. So if we take just a second this graph here, the example I was showing before, if you collect information from two nodes, no, it's too small. But what I would like to say is that there is this kind of correlation between the diameter of the network and the number of convolution you're using. Because if you use a number of convolution equals to the diameter of the networks, it means that to compute the node representation of each node, you are looking at all of the nodes in the network. And often this is not needed because there is too much information to compress into a single node. And what happened is that it's called over squashing, that this too much information goes like squashed into a unique representation and ending in having all the nodes being identical, and is not something you want. But choosing the number of convolution and the dimension of the hidden channels is not, let's say, it's not something easy to do. I hope I answered to your question.
Yeah, thanks for clarity.
So what I was saying is that up to here, the network is identical as before. The only difference is that here I'm using this global add pooling that takes in input our X, our batch, and what does it do? It simply compress all of those representation within each batch. So this sum aggregation I was showing here has been done with this simple function. Once again, we instantiate the model, we instantiate the optimizer with our parameters and the learning rate. And then we have the preview of our model. Quite simple. To finish, in terms of training and test, it's basically the same. The only difference is that right now we are not iterating over each graph. Like before, we were iterating over each node, while here we are iterating over our batches. Indeed, we are iterating over our train loader. We compute, as usual, we move the data to the device. We compute the zero gradient. We compute the output specifying the batch. We compute the loss. We compute the backward and the optimizer step. And this, it's just for updating the loss we are going to return, but doesn't matter. In terms of evaluation, it's identical. We give an input to the loader we would like to test, and we compute the prediction on each data loader, on each batch. Okay, once we have executed, we just iterate from, I don't know, for our epochs, again 50, just a sake of example, we have this test and the train. And as you can see, is much less evident with respect to before, but we moved from 0.78 in train up to 73, and from 0.52 up to 0.57. I mean, this one is, I won't expect this model working well. It's just to show you what you can do. There is a lot of work that one can do to improve this network, but it's just for a sake of example. By the way, at the end, we have for these, I don't remember how many classes there were, 2 classes, so it's not so good. We have almost 70% of accuracy in 50 epochs. And once again, we have, I'm not showing you, let's say, state-of-the-art models, but I'm trying to give you an idea of how this model works. Do you have questions so far? Because so far we saw a node classification problem and then a graph classification problem, okay? And now what I would like to show you is a real world data set. Is it okay if I go forward, or do you have questions?
The data sets that you were just using throughout this course, are the data sets were just based on images, or they were something based on textual data also?
Well, the first data set is not based on images, but is based on a citation network. So each node is a scientific article, and each link among articles tells you which article is citing another article. So in this part, the feature has been pre-computed using a bag of words that is a NLP algorithm, is a neural language understanding algorithms that converts the information of the PDF of the article into a vector. And then we are using this vector as a feature of the node. While in the second problem, we have this mutagenicity dataset in which you have mutagenicity and not mutagenicity moleculars that are basically graphs. And some of the and what you are doing is that just predicting the property of this graph. So we didn't use neither images, neither text, but we started only with graph data to be simple in some sense. Okay, moving.
I
Okay,
have
sorry.
one question.
Sure.
Is there any kind of problem we can formulate where we predict the relationship between two nodes, like where we actually predict or classify the edges?
Yes.
Would that be drastically different from the node classification, or?
No. So the idea is, well, thank you for the question, because in general, when we are talking with graphs, you may have talking about classification problem and leaving away for 2 minutes regression. We have graph classification, node classification, and link prediction. And you're right, I covered nothing so far in link prediction, but it's quite straightforward to do it for link prediction. The difference is that instead, once you have node representation, okay, you learn the probability that those nodes are connected. So for each node embedding, you try to learn the probability of those links among this one, or even autoencoders try to reconstruct the graph predicting those links, these missing links. But the model does not change too much. There are, if you go on the official library, let me show you. If you go on PyTorch in the GitHub repository, sorry, PyTorch Geometric. If you go on the repository, there is this folder with examples, and they are really easy to follow. And there are a lot of them, and you can simply look for link prediction. But the model does not change too much. And here, as you can see, there are a lot of examples, and you can have a look if you need. But yeah, you're right. The model does not change too much.
I had another question, that is, whenever we are going to use these graph neural networks for a specific task, do you have to pre-process the specific dataset that we were going to use into graph type of something information, as you have used in these examples? That is, we have to convert the data sets into graph-like structures or information.
Okay, well, it depends. If the data set is already public on PyTorch Geometric, you have simply to download it as we did it in these few samples. So with this call here, while if you have your own data set built from, I don't know, whatever you want, you have to convert it in PyTorch Geometric. And if you are interested, there is going to be right now the real world example in which I'm showing you how to load these graphs. So I think we can move in.
Yeah, that would be pretty interesting. Yeah.
Okay. So
And I had a question about what you have done, the two example, and you showed that they are accuracy of the two models. Like for the second one, it was very slow, like 70%. And usually we need it to be 80 or more than 80 even. But what regularization can you use here? And we know like sometimes we use data augmentation, but here I don't think so. We are going to use data augmentation because we already have the graph settled. But I don't know which type of regularization can we use here.
So consider that this specific data set, MUTAG, is well known in graph learning because it's really, really small. And I choose for this data set because since I'm running it on my laptop and even at home, if you want to try it, it's something that it runs. But it's quite unusual to see such a small data set, and not only small data set, but even with a small sides of the node, sides of the graph. Because in MUTAG we have really small moleculars. If you see, for example, this one is a one graph. So what we are trying to do is a complex task, and even in the literature for this type of problems, it's still low accuracy are achieved. I don't know right now which is the state of the art for MUTAG, but I don't believe it's really too high. There are many techniques one may use on this. The first idea that came in my mind is techniques related to few shot learnings, or few shot learning, or even try to think to specific null models to extend your data. So doing dataset augmentation, but it's not quite easy as you were saying. So let me say that I choose a difficult dataset, but for size the problem.
Okay, thanks.
Okay, moving forward, we
sorry,
have sure, go ahead.
With regards to regularization, I think like you can use other regularization technique like dropout, for example. The dropout you use, maybe you can also try to use some cap on the weight, so maybe the weights don't grow too large, something like that. There are like other regularization techniques other than, I guess, data augmentation that you can use to help make your model generalize.
Yes, you're right. I mean, I've used here only the dropout, but I didn't use the weight decay. And there are even much more complicated regularization techniques. And yeah, you're right. Thank you. Okay, let's move. So we have now, okay, we have our dataset. The dataset is the one I was showing you before, in which again, you think that you have a specific material, okay, and you are eating this material with a lighter, and you would like to see how the heat propagates. Okay. This is a, I mean, there is the equation of the thermal equation that tells you this. And here, what we are trying to do is to use a graph neural networks to predict this evolution of the propagation of the heat in a specific material. So
Is it something related to the molding of a material? As of, I think this is in the syllabus of mechanical engineering, something like that. If we want to heat a material to a certain point, then it changes its shape and we can mold it to any other, something like that.
exactly. But instead of doing practically, physically doing it, we are trying to use a graph neural network to predict the output.
Yeah, I think that is can also be mapped to something kind of evolution problem, which can say in case of DNA mutation or something like that.
Yeah,
We
yeah,
try to plot.
definitely. Even infections in a network, there is a spreading of information in a network and many stuff. So in this figure here, I'm showing you that there are 5 different materials that we simulate changing the parameters, but it's detail. And I don't know if you can see it, but the first graph here in the left has a low resolution. In fact, you could see the nodes, while in the most right graph, you cannot see because they are too close, so we have a much more higher resolution. What we are going to do, we just take one simple material, okay? We focus on one, we train on some of them, and we predict on the rest. Okay, if you, so here, if we abstract a little bit, we are exactly in the middle of what we did so far. Because here, what we have, go ahead.
Is this like a time evolution of the heat? How the heat spreads?
Yes, exactly.
So there's a time component to your graph in some way.
Well, we just reported the final time. We omitted the evolution during, but you eventually can introduce it, but then you have to use models that taking into account even the time dimension. While here, we just skip it for simplicity.
So is there any like a recurrent neural network equivalent of graph neural networks?
Yes, well, there is a specific direction on geometric deep learning, well, in graph neural networks that is called temporal graph neural networks. And there are many strategies, as you told, the simplest one is to have a graph neural network for each graph and then having a recurrent mechanism that collects the temporality. But then you have even much more smarter, I would say, techniques that remembers neighbors embeddings during the time and then propagates. So there are, I mean, research is going in that direction, and there is quite work around. But let's say that all of them, not all, but many of them are based on this simple message passing I've showed you today.
Yeah, okay, thank you.
Yeah, nothing. And back to us. Here we are in the middle of what we did so far, because we started with predicting node properties, okay? Then we moved to predicting graph properties. Here we are in some sense in the middle, because we are predicting the property, okay, of a node, because we would like to predict the heat on a single node, but we have multiple graphs. So we are trying to learn on some graphs and predict on other nodes, sorry, in nodes in other graphs. Moreover, this last experiment, yes, it's based on a regression, because we don't have our y is not anymore a value, is not positive or negative, is not blue or red, but it has a value. So we are moved to this regression problem. So here I don't want to lose time showing you how to load the dataset. The dataset are public available. Gabriele generated for you last week. And if you go on the repository, we have thermal blocks are CSV files. You can use the function public here to load it. And I mean, it's just a matter of running it. Here is the plot I was showing before. Let's zoom a bit on one graph. As you can see, some nodes, it's easy to see that it's a mesh, and then we can use it with a GNN, okay? And the color here represent the value on the node, the value that you would like to predict. Okay, let's start with converting to, loading those graphs from CSV files, okay, to PyTorch Geometric. Okay, what we have to do? I'm imported, well, these two are needed, let me say. And then we have from the data of Torch Geometric, we have this in-memory dataset. In-memory dataset is a class that allows you to build your own graph and load the entire graph into the memory in the RAM or in the GPU if you have a CPU available. And saying that, there is also the possibility to have non-in-memory dataset. Suppose that you have a large dataset, there are specific techniques to load part of the graph in the RAM, compute what you have to do, go back, load another part, and so on and so forth. But since this one is a simple example, I'm used in-memory dataset. We have some normalization features, and then these from utils that tells you if the graph is direct or not. We use pandas, networkx, and numpy for some preprocessing. So what we do, once again, we create this class. I call it graph reading. It inherits from in-memory dataset. The in-memory dataset require an init with a transform, a pre-transform, and a pre-filter that we are not going to use because they are basically they are operation you can do on the graph, but they are not needed now in this example, and there is too much to say in a few words, to be fair. We call the super with the init. Okay, and here we start. What we are doing? Well, basically, we are accessing for this specific dataset. We are accessing the folder for this diameter and the number of parameters that are specific on the simulation we did to build the graph I was showing to you. We use this read.
Can I know, means how did you specify the number of diameters and the parameters? Means is it known beforehand that this data set will contain this type of parameters, or is it based on what we are trying to perform, the task specific?
Yes, in particular, sorry, I closed the folder. Sorry, it's here. It's here. It's here. It's here. It's here. It's here. Okay. Here you have that we have by diameter we mean the resolution we are using, if I remember correctly, while the parameter specify the material. So this is really a let me say specific example in a sense that we generated this specific data set to show this. But if you have your own data set, of course, those are parameters you choose. For instance, we are using those data set only for loading the data. We are using the diameter and the parameter value only for reading using pandas what we do.
I understand. So you give the main directory and you use these parameters to choose the specific data set, and based
Exactly.
upon that you try to perform the work. Yeah.
Yes, exactly. Once we have loaded, we simply normalize respect to the max, the y, okay? And then we use network X to build a network X graph as an edge list, from the edge list. So suppose that here, instead of having a CSV file, you have a list of network X file. Well, then you can just use network X to load your graphs, okay? And then in this case, we are doing it manually, but we are setting the node attributes of the loaded graphs, okay? And those are just information that we have in the CSV file, and we load it manually. But if, once again, if you have your network stored with network X or GraphMLG, you can just load it, and you already have node features, add features, all the information you need, labels, whatever you need. And so this part of code is just need for read the data. Once you have loaded the data, what we do, well, we build our edge index. To build it is we are using a tensor, okay? We are iterating over the edges of our
Is the whole data set converted to graph information, or did you drop some specific columns to, and did you
in this
use some
case,
part of
yeah. In this case, we have the specific, but if you needed to remove columns, you can do it. So it's easy. And in this case, we are building this edge index for each single graph. And in fact, we build it simply using this torch tensor and iterating over the edges. We convert it to undirected using the function. And then we took the X and the Y, taking the node attributes. But this is a complex way, let me say, to do something much more easier if you already have your MLG, your network X graph. So you just need to load the graph, convert it to PyTorch Geometric, and then you have to build this data object. This data object that contain our X, our edge index, and our Y. If your GNN uses also edge features, you have also to add here, I don't know, edge attributes, and then you can put your values. Okay, so here you can build whatever you want, and finally you just append it to a list, and finally the last thing, when your list of data object is complete, you have just to call this self collate of our data list. And once this piece of code is done, okay, I forgot this. What you have to do, you have to simply call the function, the class you just defined. If you want, you can specify some transformation, and the list of transformation are available on the documentation. There is really a lot. And again, depending on the specific problem you have, on the specific task, and so on and so forth, you have different transformation. So here you have really a lot of, and each of them is dependent on the specific task you want to do. Okay, we loaded our graph. Our data set has 10 graphs. If we access to the first graph, so with that set in position 0, we have our node features, we have our edge index, we have our Y. Remember that our Y right now are, are values, so we are in a regression setting. we have the feature, we can simply move our feature to NumPy, and there are many methods to to operate on those structures. Basically, they are tensor, and you can do whatever you want with tensor. Then we are going to build the test train split. So do you remember that previously we used, in the first experiment, we used the train mask and the test mask, while then we used the 9% of the graph for training and the rest for test. Okay, in this case, we are going to use scikit-learn, the model selection of scikit-learn, to divide the train set and the test set. How it works, you basically specify that there are 10 elements. You specify the number of the test sites and a random state for reproducibility. You create your test and the train set data set, just accessing with those index. And then at the end of the day, you will have, I can skip this one. And then you can...
Is the random state value used here is also acting just like some kind of hyperparameter? You have to choose that or try it with, experimentally with the specific data set? Because normally we use 42 or something like that, I think.
Yes. So the idea is that in order to have your model as much general as possible, the idea is that you have your entire data set, you take a portion of this data set, okay, you call it test, and you move away that part. Then you take the rest and split the rest in validation and training. And here you can optimize how you split it, but the important thing is that you never test on your test set. Otherwise, it's like optimizing in the test set. Suppose that I'm writing a scientific article and I'm optimizing this value, then it means that I'm optimizing, the performance will be really, really good because I'm optimizing the test train split, but it's going to be unfair. So this is why in many journals, they requires, or conferences, they require to have multiple of those random split. Or let's say it's not a good practice to optimize the random state of train test split. Okay, once you have built it, we can build our batch size, let's see, that's one. Our data loader, the motivation why I'm using a batch size of equal to 1 is just because those graphs are quite, we are using only 10 graphs in this example. And so I'm using just one. But if we look at the batch, we have one batch. You can see that the dimension goes from the smallest graph that is 221 nodes up to 20,000 nodes. Okay, and the first one was the test, the train, and the second is the test. Again, we are going to use this batch training. Okay. Okay. The model I'm using is quite simple. The input has feature of 7, okay? And I'm using the first hidden layer to be 20, so that the first convolution moves from 7 to 20, then from 20 to 4, and then from 4 to 1. Why to 1? Because we are in a regression setting, so what we would like to predict is not a class, but a specific value. Once again, my device is CUDA, instantiating my model and instantiating my optimizer. Here, I'm also using await decay. Okay, here you can access, as I showed you before, the weights. You can access all the information. We have the same identical code for test and train. And here we have our training. So I've started my training. You can see that the losses, sorry, what I didn't tell you is that, of course, here, being in a regression problem, we are using a different loss with respect to the one that we were using before. And in fact, I'm showing you only the loss. You can see that it's starting from 0.9 and it goes from 0.8 in train, while in test from 0.9 to 0.07. So those results are quite difficult to read. What this 0.07 means. But to have a better visualization, I prepared this really small function that produces a scatter plot. So the results, I don't want to spend time on those functions. It's just a matter of printing stuff. Okay. So have a look at this training. It was really, really bad. What we expect is to have this horizontal line, okay? And the prediction is quite bad, either in train and in test. So let me try to reduce a little bit, increase the learning rate a little bit, and see what happened if we have a little bit better results. Not so much. Okay, we're stuck. Oh, I didn't. Okay, or even worse, you can see that the model is not able to predict. So how we can solve this problem? Well, let me put sorry. Let me put once again the learning rate how it was. Okay, and then I'm gonna show you, instead of using a simple GCN, we're gonna use a Sage convolution. Okay, and now it's still training, yes, and nothing on. Cool. Okay, we saw that with GCN is not working at all. Okay, what we can do, we changed the model, and what changes is simply, instead of calling a graph comb, we are calling a Sage comb. We instantiate our model, we run it, okay, still running. Okay, now you can see that we started from 1.1 and we goes from 0.06. Now, if we plot the results, they are much more better with respect to our simple GCN. And you see,
can you tell the difference between the simple GCN and the Sage version that we have just used right now?
yes, so there are the difference relies on the model. Sage has its own implementation of, you can see the detail here. So let me show you here. Maybe we have some details more. So the idea is that the convolution simply aggregates information from the neighbors, while, so what it does, it has this normalization over the degree, but it's simply this aggregation over the neighborhood, okay? While if we move to Graph Sage, that is not Chebyshev, but is this one, it has a different weight matrices for the feature of the node, okay? And of another weight matrices for the neighborhood. What does it mean? It means that, let me go back on this figure here. Okay, no, this one. Instead of having, you see that when we were computing x prime 0, we were using the same W. GraphSage use a specific W for x0 and other W's for the neighbors. And this simple modification, simple, I mean, it's another model. I'm saying simple only because from the code wise, what I did is just changing SageComb, while previous was GraphComb. So what I did, I substituted this string. But it doesn't matter. If you look at the output, it's much more much more good. Okay. And in the same manner, we can even try another architecture. For instance, here I'm using GAT convolution. What I'm doing here is there is tricky modification that depending on the number of hats you are using on your GAT layer, you have to change a little bit the size of the inner layer. But if you run it, it's going to take a little bit of time, but you may have.
Is there some kind of way we can choose means which model would best fit our respective work or specific data set, or we have to try using different models and see if this kind of that kind of process means?
Another really difficult question, in a sense that I've personally tried to work a bit on explainability, so still good results. I've tried to learn to work a little bit on explainability, and the idea. So it's another topic that Steve is gonna talk next week, but just to say you some word, what we try to do in our last work is try to explain if we can find some specific models, some specific layer that works better on a specific type of data. So suppose that you have huge node features and a particular topology, then it's better that model. Or you have I don't know, other properties of the network, and then you have to do this other model. So we weren't able to find this answer. We found other clue about explainability, but understanding a priori which architecture you may use, it's not trivial at all. You can reason a little bit on the on the layer itself. For instance, if you consider the GAT, the graph attention networks, basically what it does is to learn attention coefficients on the feature vector. So in the case you have let's say important node features, techniques like GAT may work well, or not like GAT, but based on attention on node features. While there also could be the possibility in which your input network does not have any node features. And so technique with attention on the features are not really reliable in that sense. But it's not trivial at all understanding this. And to conclude, it's the same with different other models. For instance, I have the Chebyshev, and again, I changed only Cheb here, and we have the same execution. Simply with Gene, that is another model, we have the best results. And yes, this is what I would like to present to you. I hope this gave you a general idea on how this model works, and that you can do really a lot of stuff if you get, understand how this library works. Then it's quite easy to run it. Yeah, That's all. Steve next week is gonna go through the explainability
When
part.
we get this Jupyter notebook, will you share it with us?
Yes, 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 yes. So if you go on the official page of Boumediene, there is the link to this Git repository. In the Git repository, you will find the dataset, the Jupyter notebook, and also I will put the slides, these few slides that I used. And feel free to reach if you have any questions, or feel free.
Right. Yeah, thank you very much. Thank you.
Thank you so much.
I guess you are tired, so it's better to.
Yeah.
Yeah,
A
thanks for the,
little
again
bit.
for the effort. And so, if you have questions, feel free to send him an email. And
Yes.
and he said if you go to the website of the seminar, you will see the link to the GitHub and then all the email addresses of the speakers. Yeah, thanks again. Thank you very much. Thank you.
Thank you so
for
much.
this. It was an amusing experience. Yeah.
Thank you.
We are